Hello and welcome. Today's topic, we will be discussing the physiology of digestion. So kind of understanding, how the body can take nutrients and how the body can manipulate those nutrients so that they're absorbed within the body. And then the second part of this unit, we will be discussing the basics of energy metabolism. So essentially, how can we utilize those calories in order for us to provide energy through the various systems that we have within the body. Okay. So the first thing that we want to kind of discuss is digestion. And again, digestion is the process of breaking down ingested foods through both mechanical and enzymatic activity so that they can be absorbed within the body. Sorry, let me get my notes here ready. So nutrients that are ingested are not technically a part of the body until they've been absorbed. So think of the digestive tract as kind of this pathway within the body. And in order for us to actually utilize those nutrients, we need to move them from inside of that path to outside of that path into the bloodstream in order for them to be actually utilized. So this just kind of shows us the basic system. So let me get my pointer up here, or the basic organs within this particular system. Okay, so here you can see, where the food comes in the mouth, and then it's going to travel down this tube known as the esophagus, which is shown in number 1 here. That food will then be transported into the stomach, which is shown here in blue. Once the food is kind of manipulated within the stomach, it'll then move into the small intestines, which can be shown number 6, so kind of like this purple area. And then that's where most of the absorption of those nutrients occur. And again, absorption just basically involves the movement of those food molecules from in the digestive tract to into the bloodstream. So then whatever is like left over basically will move into the large intestines, also known as the colon. And you can see that here. Here's the ascending colon, transverse colon, descending colon, and out the rectum anus area here. And that will allow us to get rid of those waste products. Okay, so again, when we think about, what are the functions of each of these individual systems? So again, the mouth and the esophagus are going to aid us in ingestion and digestion. So again, we'll start breaking some foods down within the mouth. The esophagus simply serves as a transport tube. The stomach and the small intestines will serve as a location for digestion. So again, we'll continue to break down molecules into smaller components, and also absorption. So again, within the small intestines, we will experience the movement of those molecules from in the digestive tract to into the bloodstream. Large intestines, we will have a little bit of absorption. So we'll see absorption of some of our nutrients like vitamins and minerals, for example. Also water can move in and out of the colon. And then elimination. So again, the colon will serve as a pathway for us to get to the anus so that we can eliminate any waste products. A couple organs that I didn't mention as part of this tube or this tract are known as accessory organs. So for example, we have the liver, the gallbladder, the bile duct, pancreas. Those all produce substances or store substances that will assist in the process. So those are known as accessory organs because they don't exactly follow, like the food doesn't actually pass through them. They'll just serve as simply like a helper or an accessory to the processes. Okay. Again, here you can kind of see the flow of food through the digestive tract. I would just encourage you to pay attention to these little arrows because they are a little bit light. So again, we'll start in the mouth, move to the esophagus, into the stomach, and then from the stomach, we'll move into the small intestines where there are 3 parts. So first duodenum, jejunum, and then ileum. And then next we'll have those items move into the large intestines or colon. And then lastly, we will excrete any waste products through the anus. Okay, so that kind of gives us an overview of the organs involved in the particular system. Now we're going to move into understanding how we break down each nutrient. So the first nutrient we're going to talk about is carbohydrates. And in order for us to understand how carbohydrates are digested and absorbed, we first need to understand how that they are organized. Okay. Again, as I kind of mentioned in our first lecture, Nutrition involves a lot of chemistry, actually. So I've provided you with some images of the biochemical structures of molecules. Again, not something that I'm going to ever test you on and ask you, you know, where each of these, you know, branches within the biochemical structure fall or anything. I just want you to appreciate the differences and understand that if you were to get into, you know, if you wanted to have a deeper understanding of, you know, nutrition, this is really where it starts. We need to understand kind of the biochemical backbone of these molecules. So there are three types of sugars that we have. We've got monosaccharides. Mono means one, saccharide means sugar, so it's made up of one simple sugar molecule. So for example, glucose shown here is a monosaccharide. It's made of one sugar structure. The next classification is known as disaccharide. Di means two, saccharide means sugar, so it includes sugars that have two sugars linked together. So here you can see an example. Sucrose is made up of two simple sugars linked together. And then lastly, polysaccharide. Poly means many, saccharide, sugar. Again, so we're looking at a strand of multiple simple sugars that are hooked together. There are three different monosaccharides that we should know. There's glucose, there's galactose, and there is fructose. Okay, so those are the three monosaccharides that we have. Again, basically how we consume these sugars are basically always in the form of a polysaccharide. And we're going to break them down to disaccharides and then into monosaccharides. The monosaccharides are the only molecules that can be absorbed. So we have to break down all of our sugars into a monosaccharide in order for it to be absorbed within the body. Okay. Then once I have them in the body and I decide I want to store them, I rebuild them back the other way. So I'm going to take those simple sugars and I'm going to link them together to form polysaccharides in order for me to store them within the body. Okay, so let's take a look at how this happens. Okay, so on the left here, you can see the organ associated with the digestive tract. And on the right here gives us a little summary of what happens in each of these organs. Okay, so first thing that's going to happen is we're going to put those sugars into our mouth. So again, let's think of something that's primarily sugar. So let's go with Skittles, for example. Skittles are 100% sugar. There's no other types of nutrients. There's no protein. There's no fats within Skittles. Okay, so I pop those Skittles into my mouth, and what starts happening? First thing is mechanical breakdown. I'm going to chew those Skittles up. Okay, I'm also going to secrete a molecule or an enzyme known as salivary amylase. And the salivary amylase is going to start breaking down those long strands of sugars. Okay, so a Skittle is made up of a strand of many sugars, so it's a polysaccharide. The salivary amylase is going to start chunking off the polysaccharide into smaller little sections, basically. Okay, salivary amylase will continue to work as we swallow the food and it moves through the esophagus. Again, this will just simply serve as a tube that's going to transport molecules from the mouth to the stomach. Okay, once I get those Skittles into the stomach, again, they're smaller sections of polysaccharides. I'm going to release a substance known as hydrochloric acid. And hydrochloric acid is going to actually shut off the work of the salivary amylase. And the reason for that is this hydrochloric acid is very acidic in nature. So it actually disassembles the salivary amylase so that it can't function anymore. Okay, and the reason for that is when I get to the stomach, I'm going to focus on the mechanical breakdown and the chemical breakdown of some other nutrients. So once I get to the stomach, the focus or the priority is the breakdown of fats and proteins, and carbohydrate breakdown actually shuts off. Okay, again, in our particular example, if I'm eating Skittles, that doesn't matter. We're not going to spend a whole lot of time in the stomach because I don't have any of those other nutrients. Now let's imagine that we were going to eat a peanut butter and jelly sandwich. Okay. A peanut butter and jelly sandwich has all three nutrients. It's got your protein, it's got carbs, and it's got fats as well. Okay, so it has a nice even mixture of all three of those kind of macronutrients, right? So I started the breakdown of carbohydrates in the mouth. As I transit that peanut butter and jelly sandwich down into the stomach, I'm going to shut off the breakdown of those carbs. So the bread isn't going to really be modified when I get to the stomach. The bread and the jelly, which would be pretty much just carbs. And then the protein and fats that we would find like in the peanut butter, for example, are going to be broken down in the stomach. Okay. So again, hydrochloric acid takeaway message here is going to shut off carbohydrate breakdown and allow us to focus on the digestive processes needed for proteins and fats. Okay. We will have some mechanical breakdown occurring in the stomach as it relates to carbohydrates, and this will occur through the churning of the smooth muscle. Again, if you've ever felt your stomach like, what's the word? Like growl, essentially what's going on in that particular scenario is I've got some enzymes within the stomach and it's creating this kind of like churning motion. And because there's no food in there, it kind of like creates that growling noise, basically. Okay. But basically what happens within the stomach as it relates to carbohydrates is I kind of have this churning or kneading motion of that particular organ, and that's going to kind of allow us to kind of break up those carbohydrates from a mechanical standpoint. Okay. Next, we're going to move into the small intestines. And in the small intestines, I have now broken down the polysaccharides, or those long chain carbohydrates, into disaccharides, or those two chains of sugars linked together. So I have lactose, sucrose, and maltose. Okay, so those are the names of the disaccharides. So it's an O here instead of an A, and that's the name of the molecule, right? In order for those disaccharides to be broken down, I need to have these three enzymes. I need to have lactase, sucrase, and maltase. Okay? And basically what each of those enzymes will do is take that two chain and split it off so that now I have two monosaccharides. Okay, so again, let me say that one more time. So lactose is two chains, so two sugars linked together. Sucrose, two sugars linked together. Maltose, two sugars linked together. Okay, these enzymes, lactase, sucrase, and maltase, are going to allow us to break down those disaccharides into two monosaccharides. Okay. Once those sugars are broken down into monosaccharides, or one single sugar molecule, I'm able to absorb it into the bloodstream. Okay, so when I think about absorption, again, I need to move that molecule from inside the digestive tract to into our blood. And the way in which we're going to have those molecules move is through a process known as active transport and facilitated diffusion. And I'll talk about how those processes actually work in the next slide. Okay. So now we've got all those molecules digested and broken down into those monosaccharides, or those single sugars, and I'm ready to absorb them into the bloodstream. There is a little bit that isn't going to be completely digested and therefore not absorbed, right? So I believe we said it was like 97 or 98% of our carbohydrates are digested and absorbed. However, there's 3% or 2%, I can't remember exactly off the top of my head, that's not completely digested and therefore not completely absorbed. And so those molecules are going to move on to the large intestines. If a molecule gets to the large intestines, it is going to pass through the system and be eliminated as a waste product. Okay, so again, we mentioned that these carbohydrates, or these monosaccharides, are going to be absorbed, which means they're going to move from the digestive tract into the bloodstream. And this will occur through two processes. So one process is known as active transport, and one process is known as facilitated diffusion. Okay, we have three different monosaccharides, and we're going to take a look at which ones move through active transport and which move through facilitated diffusion. So active transport, sorry, this image is blurry. I don't know how it turned out blurry in this PowerPoint, but let's talk about some of the basics of active transport. Again, let me take you back to 9th grade biology and kind of go through some of the basics of what's going on if I have active transport occurring. Okay, so some of the rules associated with active transport. I'm going to move against my concentration gradient, okay? So notice that there are not very many molecules on this side of the membrane, but there are more molecules on this side of the membrane, okay? A process such as diffusion will allow molecules to just flow down their gradient. Active transport works the opposite way. So imagine that these molecules basically have to flow upstream or against their gradient, okay? So that's step number one, or rule number one, I should say. Okay, so with active transport, I need to go against the concentration gradient. I'm going to move from a low concentration to an area of high concentration. This is good when we think about absorption of molecules, because I want to move all the molecules that I have from inside the digestive tract to into the bloodstream. Okay, this is one of the reasons why we're very effective at absorbing and utilizing carbohydrates, because many of them use active transport. Okay, the other rule that we must know about active transport is that we need to have an energy investment. Okay, so ATP needs to be invested in order for us to kind of flow upstream, essentially. Okay, so those are the major two components that we need to keep in mind when we think about how active transport works. And of the monosaccharides, two will follow this pathway. Let's see if I can write. Sorry, I don't have a touch screen, so this will be a little bit messy. We have glucose, and galactose. It's hard work trying to write without a touch screen. So those are your two monosaccharides that are going to move through this process, okay? One thing that's kind of cool about the way in which glucose is going to move is it works through a SYMPORTER system, okay? And so a SYMPORTER, get my pointer back here. A SYMPORTER basically means that I'm going to move two molecules in the same direction at the same time. Okay, so it's still going to work through active transport. I still need an energy investment in order for this to happen. But when I move glucose, I'm also going to move sodium or salt. Okay, so essentially what I'm telling you is if I have sodium, it's going to enhance the speed at which I can also absorb glucose. Okay, so now I want you to think about a product such as Gatorade, for example. It has sodium and it has glucose. And again, the reason that it's formulated that way is because this enhances my ability to absorb those molecules, and that's good. The other good thing about absorbing sodium at the same time is we know that sodium is an electrolyte. And so it's important that we have electrolytes available in sports where I'm sweating a lot. So if I'm doing something with high intensity, or maybe I'm doing something in a hot environment, or I'm doing something, for a prolonged amount of time where I might be depleting some of those electrolytes, wow, Gatorade, what a great way for us to really get a 2-for-1 benefit here. I'm going to get some of those electrolytes. I'm also going to get those sugars, and I can do so very quickly if I couple them together with whatever product it is that I'm consuming. Okay. The other process through which we can have absorption of our sugars occur is known as facilitated diffusion. Okay, and some things that are unique about facilitated diffusion, which is shown here in B, is that this is kind of a lock and key mechanism. So essentially, here's my molecule. I'm going to put it in this specialized protein ion transporter. And once it fits into this little spot, the transporter is going to flip over and allow us to dump that nutrient onto the other side of the membrane. right? So with facilitated diffusion, this process can be very, very slow because I have to put one molecule in, I flip over the channel, I dump that nutrient out. Then I flip the chamber back over, I put a second nutrient in, I flip it, I dump that nutrient back out, and so on and so forth. Okay, so with active transport, shown here, well, this is just an open channel. These molecules can just shoot through that channel no problem, like pretty fast. Okay, so glucose and galactose can flow through their channel pretty fast as long as they have ATP needed for the investment process. Okay, but with facilitated diffusion, this process is very slow. Okay, and one molecule will flow via facilitated diffusion, and that molecule is known as fructose. And there we go. Okay. So fructose will occur through facilitated diffusion. So I always remember FF. And again, that kind of helps me remember which one moves through what way. Now I want you to think about sport performance and think about which of these three monosaccharides you would like to consume, right? Do I want to consume glucose and galactose because they're going to move quickly into my bloodstream? Or would I rather use fructose that's going to move slower through the absorptive processes? Okay. And generally speaking, the answer is we don't want to go slow, right? If I'm doing something with high intensity, for example, I'm doing like an intermittent sport such as basketball, right? I'm going to take a swig of Gatorade during the timeout, and I need those sugars right away in order for me to enhance my potential performance in that particular regard. Right. If this is slow, we don't want to do that in sports. There's not a whole lot of sports where I want to do anything slow. Right. So I am going to maximize the amount of glucose and galactose that I'm consuming if it's close to performance / during the performance, even post performance, right? If I want to replenish myself, wow, let's do that really fast, right? So let's do that with glucose and galactose so that we can enhance that recovery process as well, right? So items that have fructose, such as fruits, right, are not great during a performance or immediately prior to, okay? Again, I don't want this slow release of energy because I need the energy right away in almost every sport. I would like to have that energy immediately, okay? Fruits are great for our general health, however, and the reason is we get a slow release of sugar as opposed to like a sugar spike that we might get if we ate those Skittles that we used earlier as an example, okay? So I'm not saying fruit is bad. Fruit is definitely good, and the reason it's good is because of the slow release. The reason that's bad for sport performance, so again, when I think about what I'm eating right before, maybe potentially during the exercise, and then also immediately post-exercise, I want sugars fast. So it'd be better to consume glucose and galactose because it's a faster transport mechanism. Okay, so what happens next? So again, we moved those sugar molecules, we moved glucose, galactose, and fructose via both facilitated diffusion and active transport, and they're going to move from the small intestines into something known as the hepatic portal system. And the hepatic portal system is basically like a blood vessel that's going to connect the small intestines to the liver. Okay, so it's just this specialized little one-way tube that's going to carry nutrients directly from the digestive tract into the liver. And the reason that that's important is because we want to process all of these nutrients in the liver. Okay? The liver is a freaking cool organ. It has like over 2,000 different things that it can do with nutrients. And it's also, I believe, the only organ that can regenerate itself. Like, let's say you had to get part of your liver like cut off or something. Well, that can like regenerate itself. So that's like really cool, I think. So anyway, so what I'm going to do with sugars, I'm going to carry them in this hepatic portal system to the liver. And once they get to the liver, I'm going to convert all the sugars or all those monosaccharides into glucose. Okay, so I'm going to take the fructose and I'm going to convert it into glucose. I'm going to take that galactose molecule and I'm going to convert it into glucose. Okay, the next thing I'm going to do with the glucose is decide what I need for that. Okay, so I can store it in the form of glycogen, and glycogen is just like a polysaccharide. So it's a bunch of glucose molecules linked together. So we can store it as glycogen within the liver. We can also put it in the bloodstream. And so therefore it can be delivered to like a muscle cell so that we can use it for fuel. Or it can also be taken up by a muscle cell and then stored as glycogen as well. Okay. So there's one other possibility, right? So let's say I ate like a shit ton of sugar, right? Let's say I ate a Pop-Tart, a thing of Pop-Tarts and a thing of Skittles. And now I'm just going to sit around and do work. I'm not like going to go do any type of activity or exercise. Okay. If that were the case and I didn't need those sugars, I can easily convert them into fat. Okay. So over consuming sugars will result in us storing them in fat. Fat is like the most stable molecule that I can have in the body. So our body wants to store items as fat, because it's stable and it's easy and it's safe for us to do that. Again, it's a protective mechanism so that I have that fuel for later on. Again, think about, back in the caveman days, like what if I didn't have access to food for, 2 days or whatever? If I can store those molecules as fat, I have that energy stored and available if I don't have food for an extended period of time. Okay. So again, what are my fates of those sugars? Number one, I'm going to convert them all into glucose. Then I can either store them as glycogen in the liver, or I can store them as glycogen in the muscles. I can also use them as sugar, for energy in the muscles in the form of glucose. Or I can convert those sugars into fat storage if I overconsume them and I don't need them for fuel, and I already have kind of that storage form full. Okay. So again, once glucose is put into the blood, it can be uptaken by the cells if insulin is present. Okay. Again, insulin is a hormone that's going to allow us to get those sugars into the cell so that we can either store them or we can utilize them as a fuel source. Okay. Again, we can store these sugars as energy in the form of glycogen within the muscle or in the liver, or we can convert them into triglycerides or fat molecules. So that's basically the basics of what's going on as it relates to carbohydrates. Okay, so now let's take a look at what's happening with fats. Okay, again, in order for us to understand how to digest and absorb fats, we first need to understand how they are made, right? So fats are generally consumed in the form of a triglyceride. Okay. Tri means 3. So basically I have a glycerol backbone and 3 fatty acid tails that kind of shoot off the back here. Okay. So when I consume fats, I consume them in the form of triglycerides. When I chew them up and digest them, I'm going to break them down into fatty acid tails, or like short chain, medium chain, and long chain fatty acids. And those fatty acids are then going to be absorbed into the bloodstream. And then I will reconvert them back into triglycerides. So I'll store them in the body as triglycerides as well. Okay. So again, I consume them as a triglyceride. I break them down into a fatty acid chain, and then I will rebuild them in the body back into a triglyceride if I want to store them. So again, I put this molecule in my mouth. Let's go back to our peanut butter and jelly example. So I mechanically break down the nutrient, a little bit of mechanical breakdown in the mouth, but not much going on there. Okay. Again, then that molecule will travel from the mouth through the esophagus into the stomach. And in the stomach, I'm going to release hydrochloric acid, which we already talked about. And I'm also going to release something known as gastric lipase. And gastric lipase is going to begin the breakdown of the triglycerides, and it's going to break down those triglycerides into free fatty acids and a shorter chain. So again, imagine that, get my lovely drawing skills again here. So here is my fatty acid. So again, I've got, or I'm sorry, my triglyceride. So glycerol backbone, and then those 3 fatty acid tails. The gastric lipase is gonna break it down like this. So it'll break it down into a diglyceride. So now I have 2 fatty acid tails and then 1 free fatty acid. Okay, so diglyceride and then like just a fatty acid molecule. So that's basically what's happening within the stomach. Then I'm going to move into the small intestines, and I'm going to release bile, and bile is going to help me break down those fatty acids even further. So now I've got mostly just free fatty acids floating around. So now within the stomach, let me draw you a lovely picture again. So now that bile causes us to have that glycerol backbone and some free floating fatty acids. Okay. So those fatty acids that we talked about can be short, medium, or long chain. Okay, so again, we might have like 3 short chain. Let's do 4 for simplicity's sake. 2 medium chain, and 1 long chain. Okay, so again, basically they're just quantified based on how many hydrogen molecules they have. So it's based on the chemical connections that they have within that chain, like how long it is basically, right? So they can be broken down to short chain, medium chain, long chain, some sort of combination of that, okay? And so the short and medium chain, no problem. So those we will pass through the intestine wall via passive diffusion, and they can enter into that portal system, the hepatic portal system that we talked about with carbohydrates, and then those will be transferred into the liver. The long chain fatty acids, however, can become an issue for us, and here's why. So these long chain fatty acids are going to form like a micelle. And a micelle is basically, imagine this as like this little backpack. It's this tiny little bubble that's going to curl this long chain up into like a little circle. And that long chain fatty acid formed into this micelle is then going to enter the lymphatic system. And the lymphatic system is something that we don't really talk a lot about, but it's basically like this alternate fluid pathway that's going to eventually dump into the circulation. Okay, so basically what I'm going to do is I'm going to take this long chain fat, I'm going to put it in a little backpack, I'm going to dump it into the lymphatic system, and the lymphatic system is just going to basically dump it right into the heart, right into the bloodstream. All right, and again, this is a major issue for us because it turns out if we have a lot of fat floating around in our blood, that puts us at risk for a lot of different issues. So number 1, atherosclerosis, which is basically I can have fat molecules kind of stick to the walls of the tube, and that's not good for our cardiovascular system and our cardiovascular health. Okay, so that's one bad thing that can happen. It can also clog up an artery, right? Which could lead to a stroke or an aneurysm, okay? Also puts us at greater risk for cardiovascular disease in general. Many issues come with having too much long chain fatty acids floating in our blood. And the types of foods where we get long chain fatty acids that are dumping directly into our bloodstream, turns out, are saturated fats, fats that are fried, red meats, things like that, French fries, processed foods, those types of items are not great for us because of this digestive process and what happens to those fats once we've consumed them. So we said that those medium chain and short chain fatty acids are going to pass across the membrane through diffusion. And diffusion is going to involve us moving molecules from a high concentration to a low concentration. Okay? No cost is associated with this particular mechanism, which is different than what we talked about with active transport. With the carbohydrates. So again, not much of an energy investment when we think about the breakdown of fats because of this process of simple diffusion across the intestine membrane. Okay. This shows you that those micelles that we talked about, again, don't worry about the details of this image. I like the details of this image, but don't spend a whole lot of time worrying about this. But essentially, you've got your fat molecules. We had bile released from the gallbladder, and that's going to allow us to break down those long chain fatty acids into those micelles, or those little backpacks that we talked about. Here, they're going to cross through the intestinal membrane, or the epithelial cell of the intestine. And those fat molecules are going to be dumped into the lymphatic system, which is shown here. Okay. Again, don't worry about the details of this image for this class. It's just extra info here. Okay. Again, this just kind of puts that into words. So again, we said that the long chain fatty acids are going to combine with a protein carrier. We called them micelles, but once they leave the intestines, they're known as chylomicrons. It's the same thing, though. Nothing changed. We just changed the name of them to make things a little more confusing for the average person. I don't know why. But anyway, so now they're called chylomicrons. They're carried through the lymphatic system and released into the blood. Again, that's bad for us because of those kind of health-related outcomes that we talked about. It's not great for us to have a whole lot of fat floating around in our blood. What happens to those fats once they're in the system? They can go to the cells. They can go to any type of cell to be stored for later use, or we can use them as an energy source immediately once they're kind of floating through the blood. Okay, so again, that gives us kind of the basics of what's happening as it relates to fat metabolism or fat digestion. And now we're going to take a look at protein digestion and absorption. So again, proteins, it's important for us to note as it relates to sport nutrition that proteins aren't a huge contributor for us as it relates to our energy needs, but they are important for many other functions within the body, including the building process and providing structure. So again, our proteins are going to be really important for us as it relates to allowing us to build muscle and allowing us to build many other structures within the body. They're also important for producing enzymes. So again, there's many functions associated with proteins, but two very important functions include, allowing us to build different molecules within the body and also produce enzymes as well. And enzymes are needed in order for us to break down or modify molecules from a chemical standpoint. So what happens, again, let's start in the mouth with that peanut butter and jelly sandwich. Proteins aren't going to undergo any type of digestion within the mouth with the exception of the mechanical breakdown. Certainly if I eat a piece of steak or a grilled chicken breast, I need to chew those molecules in order for me to not choke on them. So we will have the mechanical breakdown occurring within the mouth, but we're not going to have any chemical digestion or chemical breakdown occurring. Okay. Then those protein molecules are going to be transported through the esophagus into the stomach. And in the stomach, I'm going to do a couple things. One thing I'm going to do is denaturation, and I'm also going to start the breakdown of the molecules themselves. Okay. So denaturation of protein is going to occur through the use of that hydrochloric acid that we mentioned when we talked about carbohydrates. Okay. Let's talk about what denaturation means, right? So denaturation is when a protein strand is going to start to unravel. And I've got an image on the next slide to kind of show you what this means. But again, we've got to think about how is a protein consumed, how is it made, and then what happens as we ingest that molecule. Okay, so a protein is made up of a strand. Think of this as like a strand of beads of amino acids. And there are 20 different amino acids that we can consume. And so we can create different proteins based on the organization of these beads on the strand. So again, imagine a strand of beads. There's 20 different options for beads. And there are, you know, really a limitless amount of ways I could organize those beads. I can organize them in such a different way in order to get different proteins, okay? So again, imagine I have this nice strand of beads, and what I'm gonna do is I'm gonna twist it and then twirl it up and like scrunch it into a ball, basically. Okay, so that's how I consume a protein. And when I start to digest this protein, the first thing I need to do is denaturation. And denaturation basically is going to take that scrunched up ball of that strand of beads and help us to untangle the beads, right? So I'm going to kind of untangle those beads and help to get that strand out into a straight line so that each, you know, bead is kind of on its own. And the reason I want to do that is that's going to help me with this digestive process, because now pepsin has access to each little section between the beads. Okay, so again, if you think about this strand of beads, the string that's connecting each of those beads, if I have access to every single string, that's going to allow me to more effectively chop those strings up, basically. And that's what I need to do in order to digest proteins. Okay, so denaturation is just basically when I start to unravel that protein strand. And I've got an image on the next slide, I believe, to kind of show you what that means. Okay. Pepsin, again, is going to start to break down those long strands of amino acids, or the long strand of protein. Then we move to the small intestines, where the majority of protein digestion is going to occur. We're going to have some proteases and peptidases. And again, those are enzymes that are going to help us to shorten that strand. So they're going to assist in the chemical breakdown or chopping those little chunks of amino acids apart. Okay, so let me show you the next slide and kind of explain what I mean when I say it's kind of chopping up these amino acid chains. Okay. So here you can see how we consume a protein. Okay, so it's a strand of bead that's kind of all like crumpled together. Okay, in order for denaturation to occur, I need to unravel this. Okay, so first I've started to kind of unravel it here. Then you can see what's known as an alpha helix, which is just kind of like a strand, like a spiral, basically. And then finally, I have this kind of primary protein structure shown here. So these like are the beads on the strand. Okay. Again, once I have this denaturated from this configuration to this like nice strand of beads, I have access now to snip off these different sections. Okay, so those proteases, the peptidases, and that we talked about on the previous slide, we're going to nip off little subsections. So now I've got this little section. I maybe have this little section. Maybe this one goes like this. And so on and so forth. Okay. So now instead of having this long strand of beads, I chopped it up and I had like 6 different little chunks of beads, basically. Okay. So that's what's going on when we talk about what those enzymes are doing. They're creating shorter strands of these amino acids. Okay. So again, a protease is going to chop up sections. And eventually what I want to do is break down the strand of beads so that all I have are just individual beads floating around. And these are those amino acids. Again, there's 20 different types of amino acids. So I'm going to have all different types of beads when I'm done breaking down this particular nutrient. Okay. So next thing we want to do is have some absorption occurring. And again, we know that absorption is going to occur in the small intestines, primarily through that process of active transport that we talked about when we talked about the carbohydrate absorption. They're going to enter into that hepatic portal system that we talked about with carbohydrates, and they will travel to the liver. In the liver, we will have some potential modification or processing occurring of the amino acids. But actually, our final protein digestion is going to take place after absorption. So within the cells of the active tissue, those amino acid chains can be broken down into single amino acids. And again, think about, you know, building things within the body. We want to get those molecules into the cell and then decide like what exactly we need from those molecules. So we're going to wait until they get to the cells, until those amino acid chains are totally broken down into the single beads that we mentioned. Okay. So the second part of this lecture is going to talk about energy metabolism. And again, energy metabolism is absolutely, I strongly believe, is the foundation of sport nutrition. So it's super important for us to understand what is energy metabolism and how can we apply this to various sports depending on the demands of that particular sport. Okay. And then the last thing that we can do is then take this information about what we know about nutrition, digestion, and absorption, and how can I apply that then based on the demands of each individual sport as it relates to these metabolic pathways, these metabolic processes. So the knowledge of energy metabolism is going to enable us as sports nutrition professionals to assess the potential effectiveness of a variety of nutrient supplements as it relates to timing, type, and amount of, you know, calorie intake and types of calories as well, right? So this is important for the education of our athletes so that we can help them to best understand what they need to do to fuel for success and also recover from a hard performance or a hard practice, et cetera, things like that. So, all right. So I think we'll stop there, and I will finish up this lecture as a second part. So you'll kind of have two different videos for this lecture. All right. Have a great day. Thanks.